The year was 1984. My Detroit Tigers won the World Series, and kids were taking AP Physics C mechanics exams. So let's punch one of these out. Question one says the torque is the rotational analog of, that's going to be force. If you think about F equals ma, the rotational analog of that would be like moment of inertia times angular acceleration, and that's going to be torque. So torques cause angular accelerations, forces cause linear accelerations. So answer number one is going to be D. Let's try another one. Looks like we got something rolling off a table here. Probably some kind of kinematics or something going on. Let's see what we got. Object slides off a roof 10 meters above the ground. Initial horizontal speed of 5 meters per second. The time between it leaving the roof and hitting the ground is most nearly. Well, the horizontal motion doesn't even matter. So you're really just going to be looking at this vertical motion. It's going to be basically kinematics. Delta y is 1/2 at squared. And so it looks like we're moving, we'll make positive down 10 meters, 1/2 of 10 times t squared. So 10 equals 5t squared. So that's going to be 2 equals t squared. So it looks like it's going to take like root 2 seconds. Looks like for number 2, we're going to get C for the answer. Root 2 seconds. Let's see what we got next. Simple pendulum of length L, bob mass M, oscillates period T. Oh, this is if you mess with the mass on a pendulum. This one's a gotcha because with the pendulum, the period goes like 2 pi root L over G. There's actually no dependence on mass. They try to get you with this one all the time. So that one's going to be C. It's just going to be have the same period. All right, looks like we got a little motion graph over here, a couple cars. Let's see, time t equals 0. Let me make this a little bigger. Time t equals 0, car X is traveling a certain speed. Okay, it just goes constant speed. Car Y is just constant acceleration. They pass each other here, okay, at t equals 0. Both cars travel 2 parallel lanes, same straight road. Okay, and there's the graphs. What's going on at 20 seconds? So 20 seconds, car X has been cruising at this high speed for the full 20. Car Y has been speeding up. So let's see. Car Y is not going to have gone as far, right? The area under the curve represents how far it's gone. So car Y has only gone like triangle worth of area, and car X has gone rectangle worth of area. So car Y is will not have gone as far. So what does that mean? That means that car Y will be behind car X. So that is going to be A. So number 4 is going to be A. Number 5, from t equals 0 to 40, the areas under the curves are equal. Well, the area under the curve represents how far it's gone. So it means they should really be at the same place. Let's see. Yeah, car Y is passing car X. And so the 5 is going to be B. Because the area represents how far they've gone. All right, next page ready? Let's see what we got. Ice skater spinning about a vertical axis with the arms fully extended. If the arms are pulled in closer to the body, which of the following ways are the angular momentum and kinetic energy affected? Well, the idea here is, so the skater's on the ice. And so there shouldn't be like really external torques on the system. Nothing making the external that's making the skater go. So angular momentum is going to be just conserved. So that's going to remain constant. So it's going to be down to C or D. And then as far as the kinetic energy, when the skater pulls his or her arms in, that's basically doing work. So you're pumping joules into the system. And so the kinetic energy of the skater is going to go up. So the right answer to this is the angular momentum is going to be constant, but the kinetic energy is going to be increasing. So that's going to be C. 6 is going to be C. Another way to see that is, so I omega, which is the angular momentum, that needs to be constant. When the skater pulls his or her arms in, the moment of inertia goes down and the angular momentum goes up by the same factor. As far as the kinetic energy, that's going to be like 1/2 I omega squared. Well, I goes down by a certain factor and omega goes up, but the omega gets squared. So the effect of the omega going up is going to be greater than the moment of inertia going down. So this guy is going to, the energy is going to increase, and so that's why that one's C. All right, what's going on next? Let's see. The parabola above is a graph of speed v as a function of time for an object, which represents the magnitude of f as a function of time. So the velocity is going like t squared. So acceleration would go like the derivative of that. So the acceleration would kind of go like 2t. And then force would be proportional to acceleration. So the force should grow linear with time. So are any of these doing that? That's going to be E. So 7 should be E. 7's going to be E. All right, let's see what we got next. Number 8. Object of mass m lifted, constant velocity, vertical distance h, and time t. Well, they want to know about the power by the supplied by the lifting force. Yeah, power is just energy per time. Energy per time. Yeah, constant velocity, vertical distance h. Oh, so the energy, we've just lifted it up by mgh, and then the time that it required was t. So it should just be mgh over t. So that's looking like number 8 should be B. Yeah. All right, looks like we're pulling a couple boxes here. What's going on? Frictionless system, we're pulling it. Oh, I just want to know the tension in between this thing. Okay, so let's see. We have F. Let's look at the whole system. If we look at the whole system, we could do basically F equals ma. So you'd say F equals like 3 times the acceleration of the whole system. So the acceleration of the entire thing is going to be like F over 3. Then what we can do is go to just the 1 kilogram mass, just this one, and the thing that's accelerating is just going to be the tension. So if you do F equals ma on this, sum of the forces is ma, the tension is the only force accelerating this thing, and the mass is only 1, so the tension is actually just going to be numerically the same value as the acceleration, so it looks like it's going to be F over 3. So that one should be 9, should be E. This one's E. All right. Already on number 9. Let's see what's next. Next page. 10 to 12. It's a bunch. Let's see. Cylinder rotates with constant angular acceleration. Okay, this is rotational kinematics probably. Cylinder's moment of inertia is 4 kilos meter squared. Kilograms times meter squared. Starts at rest. 1 radian per second at 2 seconds. Oh, it wants to know the angular acceleration between 0 and 2. Well, that angular acceleration, alpha, that's just basically your change in angular velocity with the change in time. And so that guy is just going to be, what did we do? We went from, it was at rest. So we got to 1 radian per second, and it took 2 seconds to do it. So it looks like it should be 0.5. So 10 ought to be A. 10 is A. Let's do this one. What's the angular momentum at 2 seconds? Angular momentum, if you forget, so linear momentum is mv. Angular momentum is the angular version of that. So that's going to be like I omega. And so what is this thing? It's a cylinder. Oh, we know the moment of inertia. Moment of inertia is 4. In the t equals 2, the angular velocity is 1. Oh, wow, so it's just 4. So 11 should just be D. It should just be 4 times 1. That's going to be D. Yeah, 11's D. That one wasn't tough. That one wasn't too tough. Let's look at number 12. What's the kinetic energy at that time? That's just 1/2 I omega squared. The way that you can remember that is for translation, that's like 1/2 mv squared. And you just want to do the rotational version of that, 1/2 I omega squared. So that's going to be half of 4 times, what did that thing say? It was going 1 radian per second. So that's going to be 1 squared. So that's just going to be half of 4 or 2. 2 joules, so 12 should be B. Right on. let's do 13. Oh, this thing called an Atwood machine. Two objects with masses M1, M2. M2 is heavier, and you release it. And they want to know the total linear momentum of the system. When the speed of each object is v. Okay, so that's just momentum. Remember, momentum's a vector, and so what's going to be happening is pointing in what do they want? The magnitude. Okay, so M2, the momentum of M2 is going to be M2v that way, and the momentum of mass 1 is going to be M1v that way. This one's going to have the larger momentum, I guess, so if you choose, say, positive being down, you would say it's like M2v minus M1v. So it's going to be M2 minus M1 times v. So it looks like B is the answer on that one. So 13 ought to be B. So let's see what else. We're asking more about this one. When M2 has gone down a distance h, the potential energy of the system has decreased by how much? They want to know. So the deal here is that if M2 goes down by, they want to know how much the potential energy has decreased by. Well, the point being that M2 will have lost M2GH. M2 will have lost that much. M1 will have gained M1GH. Right, so we lose that and we gain that. And so they basically want to know how much we've lost. So we'll have lost the amount that's that one minus that one. So it should be this one minus that one. So the answer is going to be M2 minus M1 GH. That should be A. 14 ought to be A. Right, let's see what we got next. We're on number 15. Following graphs, all drawn on the same scale, represent force as a function of distance. So remember, the area under is going to be the work. Let's see. Which graph represents the force that will cause the greatest change in kinetic energy? Well, that's going to be the one that has the greatest area underneath. So you just kind of count boxes. These two are going to have the same. Oh boy, let's see. Oh, there must be a fifth one there that I've got obscured. Oh, it's got to be this one. That one has the greatest area. So number 15, that one should be E, because you just want the greatest area. So answer to 15 is going to be E. Well, what's next? Let's see. Square piece of plywood. We're getting pushed by a couple forces. Okay, right. So this thing, yeah, it looks like there's going to be a net force of 5 upwards, and this thing might start to spin. What are they going to ask? Let's see. Where should a third force be placed to put it in? Oh, in equilibrium. Yeah, you just need the torques to balance and the forces to balance. So you want to kind of put that guy over there. That's good. That'll do it, because then it won't be able to rotate either way, and it won't be able to translate. So that one's gonna 16 should just be A. Yeah, that one's A. If you put it in other positions, the thing's gonna spin. So that's why none of the other ones are any good. All right, let's see what we got. Here we go. 2 particles, equal mass, moving with equal speeds. Okay, so they're coming in like this. They collide and stick. Their velocity after the collision has what magnitude? So looks like your vertical momenta are gonna like cancel, so nothing's gonna be going on vertically, and they're gonna just have this sort of horizontal motion, I guess. And so what you can do is you can look at the momentum before in the x direction equals the momentum after. We don't even have to worry about the y direction. And the momentum before in the x direction, that's going to be, it's just going to be this component of mv, right? The component that goes this way. So that's like, oh, this is 30. So that's going to be like mv sine 30 or cosine 60, either way. So just for this one, for just one of them, it would be mv sine 30. So this is going to be 2m naught v naught sine 30 equals, and now what do? They stick together? They stick together, and so then it's going to be, the final mass is going to be 2m, and then it's going to be times some v final. So v final then must be, well, the 2m naught will cancel, so it just looks like it's going to be, yeah, v initial sine 30, which is half of v initial, yeah? So that's right. So this one, 17, should be B. Number 18. Which of the following is true for a system consisting of mass oscillating at the end of a spring? Let's see. Let's just go through one by one. Kinetic and potential energies are equal. That's ridiculous because sometimes it's moving and in the dead center and has no potential energy. And sometimes it's way out at the edge, so it has lots of potential energy but no kinetic. So that one's ridiculous. They're both constant. No, again, that's silly. It's changing all the time because the speed's changing. Maximum potential energy is achieved when the mass passes through equilibrium. No, that's when it's going the fastest. So that C's no good. Maximum KE and maximum potential energy are equal, but they occur at different times. Maximum K, that's actually true. This is going to be our winner. So we could quit there. D, that one, 18 should be D. But let's just check this one for fun. Maximum KE occurs at maximum displacement. Already that's bad, because when you're way out at the edge, that's when you're like not moving. So this one's a loser. So 18 is going to be D. All right, what's next? Let's see, 18, we're on 19. We got something going in a circle, radius 2 meters. Oh, and here's the angle. Okay, gotcha. The speed. Oh, okay, so this is one where you want to do like V equals R omega, and we got to figure out what the omega is. Well, the omega is going to be d theta dt. It's the rate of change of the angle. So omega itself is going to be d theta dt. So we got to take the derivative of this thing. So 6t plus 2. And what do they want to know? You want to know it at 4. The speed at 4. So when we get to 4 seconds, 6 times 4, 24, plus 2, that's going to be 26. Okay, so that's your angular velocity. And then we've got to come up here and just check the speed. Well, what's the radius now? 2. So we've got to go 2 times 26, should be 52. So that guy looks like D. Number 19 should be D. 20, mass of planet X is 1/10 that of the Earth, and diameter is 1/2 that of the Earth. They want to know acceleration due to gravity at the surface. What I'd like to do, I'm kind of something like this, is here's the Earth or whatever, here's a person, and you want to find the force on that person. Well, the force on that person would be like gravitational force times the two masses, mass of the Earth, mass of the person, over radius of the Earth squared. But that's going to be equal to ma. That's going to be equal to the mass of the person times a. So the mass of the person will cancel. So acceleration in general is going to be gme over re squared. And so now what we got to do is just kind of compare, see what happens. So what's going on? We go to some planet where this gets to be 1/10. So 1/10, that's actually going to knock down the acceleration by 1/10. And then what else happens? And then the diameter is 1/2. So that means the radius is half. If the radius is half, that means we get an extra 1/4 in the denominator. So that would be like 4 times bigger. So first we got to cut it by a factor of 10, but then we got to multiply it by 4. So it's going to be 4/10 of what it used to be. So it's going to be 4/10 of the old acceleration. Well, the old acceleration is g, or about 10, so it's 4/10 of 10. So it's 4/10 of 10, so that's just going to be like 4. So the winner should be 4 meters per second squared, so 20 ought to be B. Let's do 21. says person pushes a box across horizontal surface, 0.5 meter per second. Box is 40 kilos and there's some friction. And they want to know the power supplied to the box, by the person. So really what's happening, I guess, is as you're pushing it, friction's continuously doing like work back on you. And so what do we got going? So every second, like the work done by friction is going to be like the friction force times the distance. So the work done by friction is going to be like mu mg coefficient times normal force times the distance. So what is this thing? Coefficient is 0.25. With mass is 40. G is 10. We take it to be, and it goes like 0.5 meter. So what do we got? A quarter of 40. That makes 10. 10 times 10 is 100, and then half of 100 is 50. So there's like 50 joules, and that would be like in a second. So 50 joules per second is 50 watts. So 21 ought to be C. Let's see, 22. Uniform bar, weight W, supported horizontally like this. They want to know the force at this point. Oh, they just want to know the direction. Got it. So, okay, well, if you draw this force, there's a tension that's going that way, and then you'd have like the mass of this thing, the weight going down. So there's mg, there's t. So this thing's not moving around. So whatever happens, let's see. First of all, there has to be a component, at least, of this thing that goes that way, because you have to fight the leftward component of this thing. And then also, we can't be like pulling down here, because then this thing would rotate. So we have to have a component that goes up like this. So it's going to have to be like to the right to fight the horizontal part of this, and it's going to have to be up to keep it from spinning. So you have a component that way and that way, so it's going to have to go kind of diagonally up like this. So it looks like our winner is B. So 22 is going to have to be B. $23. Looks like we got mass bouncing on a spring or something, or hanging. Let's see, 0.1 kilos, initially unstretched, 40, K is 40. The block is released, and they want to know the amplitude of the motion. All right, so what do? Do we release it from rest? Oh yeah, we release it from rest. And so it's attached to it's initially unstretched. I think we can do energy with this thing. So what you can do is say that let's take, so it's gonna fall eventually some height. So right, so let's call whatever lowest point that it gets to, whatever the lowest point is, we'll call that like height would be 0 down there. So it's at some height right now. mgh. So that's kind of like its energy before. That's the only kind of energy it has before. And then when it gets to the bottom, it's going to be at like height 0. And the only type of energy then that would be present, and it won't be moving again. So the only type of energy that will be present will be that spring potential energy, 1/2 kx squared. And so that's going to be how far it gets from this unstretched or equilibrium location. So that is going to be the amplitude. So I think we can probably start plugging in numbers. So what do we got? 1/10 of a kilo. This thing is, G is 10. Height is what we're looking for. 1/2 of 40. And then the amplitude itself actually is this height. So that's like h squared. So this is going to be 20h equals, what is this? Equals 1. So h is going to be like 1 over 20 meters is going to be the, that's going to be how far down it's going to fall from this point. Let's see. So then, but it's never going to go this high again. Hang on. So this h, this is actually double the amplitude. So we just found that h is 1 over 20 meters, but the amplitude then is going to have to be 1 over 40. Ooh, that's a nasty one. Yeah, because it's never going to get higher than here, and it's never going to get lower than that place where it turns around. So this height that you find is going to be double the amplitude. So the h is 1 over 20. That means the amplitude is going to be 1 over 40 meters. So that's going to be A. Okay. That was probably the sneakiest one so far. Let's see. 24. At what time after release will it return to its initial position? That's just code word for find the period. So for a mass on a spring, that goes like 2 pi root m over k. The way I figured out which one goes on top is if something's heavier, it's going to take longer to bobble it back and forth. So this is just kind of plugging and chugging. So let's see, this is 2 pi root, the mass was like 0.1, k was 40. So what is this? That's a tenth, and then divided by 40. So that's like root 1 over 400. So that's going to be like, there's going to be like a root, root 20? No, root 20 in the bottom. So it's going to be like 2 pi over 20. So that's going to be like, that's going to be pi over 10. So 24 ought to be C. There's that one. A couple more, almost done. What are we on? 25. Particle moves in simple harmonic motion, represented by the graph above. Which of the following represents the velocity as a function of time? Well, let me see what's being graphed. Oh, this is position. Got it. So, okay. So the position's moving like this is like a cosine function because it starts at maximum. So your x of t is going to be like 4 cosine of some stuff. Let's see, what's the period? This is 2. It repeats every 2. So cosine blank t, cosine of something t. So let's see. Oh, all these have pi in them. This is actually then going to be pi because, let's see, if you put in t equals 2, it repeats. That makes sense because if I plug in t equals 2, yeah, so this is the correct position function. Then velocity is going to be the derivative of that. So you just got to take the derivative. So equals derivative of cosine, negative signs, you get negative 4 pi sine of pi t. The pi comes out when you take the derivative, so that should be, 25 should be E. What I was doing here was just checking that I had, that this was correct. So when t equals 0, you are at 4. And then the very next time it repeats, after it does 1 repetition, you're at 2 seconds. And that's when this argument gets to 2 pi. So, you know, cosine goes 0, it starts at a maximum, and then the next time it gets to that maximum is going to be and this is 2 pi. So this lets you know that this is the right format. Okay. 26. What's happening here? Let's see. Constant speed along this line. Magnitude of angular momentum with respect to the origin. Okay, this is the origin. So angular momentum, mv_r perp, or mv perp r, but this way is probably the easiest. So it's just going to be mv, and then the only part that matters is the perpendicular part of r, which is, this is your r perp, which is a. So it's going to be mva. So 26 ought to be B. So there's that one. 20, we're on 27. Uniform stick, length L, moment of inertia, I naught. So here's the stick. Around here, it's I naught. Particle mass M attached to one end. The moment of inertia, the combined system about the center. Oh, it's still about the center? Well, all you can do is add a point mass to it. It's attached to one end. Oh, got it. Okay, so this length is L over 2. And you put the mass there. So the additional moment of inertia from that point masses go like mr squared. And so it's going to be like m, but then your radius is L over 2. So it's going to be like mL over 2 squared. So that's mL squared over 4. And we got to add that to the original. So you got to add that puppy to I initial. So it looks like it's this one. 27 ought to be A. (28). Body moving positive x direction passes the origin t equals 0. Okay. Constant speed. Then we do constant acceleration. Oh, we just want to know where it is. Oh, this is kinematics. So let's see. For the first second, we're going 24 meters per second. Okay, so from t equals 0 to t equals 1, from t equals 0 to 1, during that time we just go we go 24 meters. So we'll store that in the bank. Now we got to get the next part. At t equals 1 second, it's given a constant acceleration in the negative x direction, and then they want to know the position after 11 seconds. Oh boy, so let's do this. We can say our delta x is 1/2 a t squared plus v initial t. And what we can do is we can say, okay, so our delta x is going to be 1/2 of, what's the acceleration? In the negative x direction. So it's half of -6 times, now how long do we have to do this? T equals 11. Okay, now this interval, we're going to just use 10 seconds. It starts at t equals 1, goes to t equals 11. So this is going to be 10 squared plus, what was our v initial? We were going 24, yeah? 24 times 10. We're going to do that for 10 seconds. Okay, so this is going to be, let's see, that's 100. 10 squared is 100. This is going to be like -300 plus 240. So, oh, I see. So during this interval, we back up -60. So what we have to do is we got to go forward 24, but then we got to back up 60. So this is during like interval 1. This is during interval 2. So if we go forward 24, we got to go back 60. So not only will we go back to the origin, but then we're going to have an extra 36 left over. So it looks like it's going to be C. 28 should be C. (29) Center of mass of a wire kind of bent like this. Okay, so what you can do, we're trying to find like of course the horizontal center of mass is along this midline because of the symmetry, but what we can do is we'll find the vertical center of mass. Well, what we have are basically 3 objects. You've got M, and we'll just say that they're kind of like, each one is like a kilogram or unit mass 1. So what we can do is we can say, up at position L over 2, at this height anyway, at L over 2, we've got 2 masses up there. So it's sort of like position L over 2, that's worth 2, and position 0 is worth 1. So position L over 2 is worth 2, position 0 is worth 1, and then we have to divide by the total mass, which would be like 3. And so what we get is L plus 0 over 3. And so it looks like it's going to be L over 3, which is going to be, where do we have that as an option? Let's see. So this is L over 4. It's going to be B because it's like bigger than L over 4. It's L over 3. So 29 should be B. Yeah, 29 I think that's going to be B. It's going to be this guy. All right. We're on 30. What do we got? 6 more to go? 30. Racing car going around a track. We're looking from above. At the instant when the car's velocity is directed which way is it going? It's going, hang on a second, moving around a track. At the instant when the car's velocity is directed east, the acceleration is due south. Well, okay, if we're going in a circle, the only time the thing could be this way, or the acceleration could be this way, is if you're up at the top, because the acceleration is toward the center. And what else is happening? at the instant when the car's velocity is east. Oh, okay, so v is that way. Great. So when viewed from above, well, first of all, we know we're going clockwise. So it's got to be one of these two. And then, and then the other thing is that it's, and the acceleration, the centripetal acceleration, is v squared over r. So what is it? 3 is the acceleration. The equals v squared over, what was the radius of this thing? 300? V squared. So v squared is going to have to be 900. So v needs to be 30. So it looks like 30 is going to be, or 30 is, the answer is going to have to be A. So 30 is A. And let's do 31. 31. Mass M1 is moving with speed v towards stationary mass M2. Okay, so here's M1 on the move. M2 is just sitting there. The speed of the center of mass of the system is. All right, so what you can do here, easy way to get there is velocity at the center of mass is what you can do is it's basically like mass 1 times speed 1 plus mass 2 times speed 2 over the total mass. So it's kind of like a weighted average of the velocities. So what you can do is go, what do we got? Mass 1 is moving speed v1. This guy's not moving, so that term is 0, plus 0, all over the total mass, m1 plus m2. So it should be m1 over m1 plus m2 times v. So it looks like 31 should be E. All right, just a couple more. (32) 100 Newton weight suspended by 2 cords. Tension in the slanted cord is something. All right, let's see. This is going to be 100 down because of gravity pulling. That means that the vertical component of this guy needs to be 100. Otherwise the thing's gonna wipe out. So any answer so this thing not only has a rightward component but an upward component. So these answers are bad because it needs to be like at least 100, right? So then, well, if that's 100, this upward component is 100 newtons. I guess I can even put it there. And so then that's like the opposite side here. And so to get the component that's here, it's kind of like mystery number sine 30 equals 100. So it's like t sine 30 equals 100. Well, sine of 30 is 0.5. So t times 0.5 is 100. So that means t's got to be like 200 newtons. So that should be D. 32 ought to be D. Let's do 33. 33 looks like it's going to be easy. Let's see. Particle will move such a way. X is, this is position as a function of time. Okay, they want to know the KE. KE goes like kinetic energy is 1/2 mv squared. So it goes like v squared. So really what we do need to do is figure out how velocity goes. Well, if x goes like t to the 3/2, if we take the derivative, v is going to be like, taking the derivative, it would be 3/2 t to the 1/2. Okay? But then when you square v, so v squared is going to go like this thing squared. So it's going to go like t to the 1st. So it's going to be linear in t. So it's going to go like 33 should be C. And then we're almost done. 2 more. Here we go, 34. Top of a 70-meter high building, 1 kilo ball thrown downward 10 meters per second. Okay, so 10 meters per second, 70 meters. If the ball reaches the ground with a speed of 30, the energy lost to friction is what? Oh, okay, so we should see how fast it would have been going without the friction, and then right, and then we can compare. Oh, never mind, I take that back. Let's do E before at the top, the total energy before. that's going to be 1/2 mv at the top squared plus mgh, right? So that's going to be like 1/2 of, what's the mass of this thing? 1. Oh, it's only 1. And the speed at the top was 10. Okay, so that's, I'm leaving the m out because it's just 1. Plus, and then 1, and g is 10, and h is 70? No, 70. So your total energy, your joules you have to play with, it's half of 100, which is 50. 50 plus 700, so it looks like what? We got 750 joules to play with. Okay, now at the bottom, let's look at our E after. That's just going to be 1/2 mv squared. So that's going to be 1/2 of, again, the mass is just 1, so I'm going to leave it out. The V, this is 30. So V squared is going to be 30 squared, or 900. So so that's going to be half of 900 is 450. So joules. So it's like it should have had 750 total at the bottom, but only has 450. So that means there's a discrepancy of 300. So it looks to me like we lost 300 joules to friction. So that one should be C. 34 should be C. And now we've got the very last question. Here we go. Light, rigid rod, masses attached to the ends, release from rest. The rod begins to rotate with what angular acceleration? So you need to know what the torques are on it to learn how it accelerates. Let's see. Here's the pivot. Attach the pivot. Okay, so you're going to have this guy pulling down with a force like 3m naught g, and then this guy's going to pull down with a force m naught g. So your torques are going to be, well, force times distance. So you're going to have 3m naught g times L. That's your torque going that way, going counterclockwise. And then clockwise is going to be this torque. You're going to have m naught g times 2L equals. Okay, now we got to work on the, so that's on this side, the torque. Let me just quick get this. This is 3 m naught gl minus 2 m naught gl. So this is just m naught gl. Okay, equals. Let's do what that equals. Well, the moment of inertia is going to be, it's light rigid rod, so we ignore the rod, we just do the point masses. So the 2 point masses are, it's mr squared for each mass. So this mass is 3m naught, and the distance that goes with it is L squared. And then we have to add to that mass m naught plus, or times the distance of 2L, but then entire quantity squared times alpha. So you have m naught gl equals, okay, we got 3m naught L squareds plus 4m naught L squareds, because 2 squared is 4. So this is going to be 7m naught L squared alpha. M naught G's are gone, or M naught's gone rather. And so this is going to be like G over 7L equals alpha. Is there something like that? G over 7L. 35 should be A. Right? And that was the year 1984.